Okay, good morning. So let us start today's lesson. Actually, this would be the last topic here, but then if we have more meetings, we can solve more nice problems. Okay, so I want to start with something here. Of course, I want just to motivate you a little bit. This is not the real proof or the real reason behind that, but I want to make it a little bit understandable. So let us start with two functions here. I introduce you a function f of, for example, let us consider the variable is nu. Okay, so f of nu is equal to, this is the Greek letter nu, okay, nu. And then this is, I define it as e to power I times nu. I am assuming that nu is a real number here. Okay? And then I introduce you another function, g of nu, and then I have defined it in this way, cosine of nu plus I sine of nu. So it's crucial to realize that I'm assuming that this nu is a real number. So let me just differentiate it. Of course, if I want to differentiate a function in a complex numbers, I need to first define what do I mean by differentiation in the world of complex numbers. But I told you that this is not the real proof, but that's better than nothing, you know. So let us just take a derivative, assuming that all the rules will apply here. So the derivative of cosine of nu is minus sine of nu. By the way, if you remember, we talked about this before, that the derivative of cosine becomes minus sine if nu is expressed in radians. If it is in degree, the formula is not that simple. So they will have an extra factor. So this is one, it's crucial to assume that nu is a real number. So it's expressed in radians. And then if I differentiate this one, the derivative of sine is cosine. So what I do now, I factor an I out. This becomes minus 1 over I sine nu. This becomes cosine nu. But of course, 1 over I, what is this 1 over I? It's minus I, agree? We had this before. Why? Because I times minus I becomes minus I squared, and minus I squared is equal to 1. So that's the reason. 1 over I is always negative I, but there is an extra I negative sign here. So it becomes positive I sine nu plus cosine nu. So let me write it the other way around. So it becomes I, and then it becomes cosine nu plus I sine nu. Yes? So what happens? What happens? I differentiate this function. It becomes the same function with an extra factor of I. Yes? So this becomes I times g nu. So the function that I have introduced you here, when I differentiate it, it becomes I times the function itself. Yes? So what does this mean? This means that if I divide g prime of nu by g of nu, it becomes a constant. Yes? The constant I. Okay, so what can I write for the left-hand side? This is for me. This should be familiar with your eyes. Yes, g prime g as a fraction. This is the derivative of ln of function. Yes, ln function. So this means that I can write it in this form. Yes. And now I have a function. I don't know what that is, but I know its derivative is constant I. So what can I conclude about this function? I can conclude that this function is equal to what? Can you say me? So the derivative of a function is I, assuming that everything is like real numbers. So what can I conclude about ln of g of nu?
It's equal to xi.
Not x, here nu, yes? X nu I, but plus a constant, yes? We don't know what that constant is yet. Okay, but I am looking for g of nu. So what happens? G of nu, ln of g of nu is that expression. So if I ask you what is g of nu itself, so you will say this is e to the power of this. Yes? And then I can write it, for example, as e to power I nu times e to power c. But e to power I nu is now f of nu, yes? So this becomes f of e to the power of c, f of nu. Yes? So we realize that g of nu is not that different from that function. I'm telling you, this is not the proof at all. I'm just trying to motivate a little bit, because if I just write the formula down, it becomes coming. It should be a little bit surprising. So what we did, we just wrote two functions here. We didn't do with anything with this function. We just start doing something with that function, and then we motivated ourselves somehow that the relation between this function and that function is like that. Yes, but if, of course, if this is this relation known, no yet, because C is not determined yet. But if this is going to be valid for all choices of nu, this should also be valid for any particular choice of nu that I make. Let me check. So I would say that this formula is also valid, should also be valid for choice of 0. Yes, let me. So this relation apparently seems to hold for any choices of nu, because you see that I have just started with a typical u and I calculated and I got this result. Yes. So what we can say that because this is true for all choices of nu, this is also true if I choose nu equal to 0. But if I choose nu equal to 0, what happens for g of 0? This becomes cosine of 0 plus I times sine of 0. Sine of 0 is 0, cosine of 0 is 1. So g of 0 is nothing except 1. E of c is just E of c. But what is f of 0? F of 0 is also 1. Yes? So this gives me that e to the power of c is nothing except 1. And I don't care about c itself. I just put it back here. What I get that there is no difference between g of nu and f of nu. Yes, it's a good motivation. I'm not saying this is a proof, but this is a good motivation that actually these two functions are the same. Yes, so there's no difference between this function and that function, and that's a very, very important formula in complex numbers. But let me emphasize again here that nu should be in R. So nu is in radians. Yes, so that's a very nice formula. Okay. Any questions so far? Yes?
Do these functions have a graph you can draw?
No, graphing the function, it needs 4 dimensions. Yes, because when you write a function, y equals to f of x, so you have an x-axis, but you have a y-axis, yes? But if you write a complex function where w is a complex number, and then z is also a complex number, for representing z, you need 2 axes, yes? The real axis and the y-axis, and the same thing here for this one. So you need to have 4 dimensions, actually. So this is why the graph of complex numbers are not that common, but we can have 2. Mapping is actually a notion for complex numbers. So we can call this z-plane. So it means that I denote a point, and then I can consider a w-plane, and then I try to understand what this function will do for me if I take one point from this a complex plane to that point to a complex plane. But if you want to visualize it as a graph, as we do it for normal graph, it's not possible because we need 4 axes, yes? 2 for the variable z and 2 for variable y, yes? Okay. So let us now, this is probably by many mathematicians is called the most beautiful equation in whole mathematics. That is called, again, Euler's identity. Yes. So if let us replace nu by pi. Yes. So this becomes e to power I pi is equal to cosine of pi plus I sine of pi. But if I ask you what is cosine of pi, it's 1. And if I ask you what sine of pi is 0, this becomes -1. And then when you move it to the left, it becomes e to the power I pi plus 1 equals to 0. So by many mathematicians, this is the most beautiful identity in whole mathematics. Why? It's good, by the way, because first of all, it's simple, yes, and then it contains more or less all fundamental constants in mathematics, yes, 0, 1, I, pi, and e, all in one single equation. So people think that probably this is the most elegant equation in whole mathematics. So e to the power of I pi plus 1 is equal to 0, yes? And of course, if you want, you can calculate something else. But remember, I am not able to calculate e to the power. So this is ridiculous to write, 45 degrees. So, okay? So this, you have to express everything in radians if you want to work in this context. So for example, if I ask you what is e to the power of I pi over 4, then you can calculate it as cosine pi over 4 plus I sine pi over 4. And then cosine of this one is just 1 over square root of 2 plus 1 over square root of 2 multiplied by I. So if I want to write this in a standard form, the standard form of this is this one. So that's a complex number. For example, if I ask you, what is the real part of this? Be careful. So this is a complex number. What's the real part? You see, the real part is 1 over square root of 2. I can ask you, what is the absolute value of this, by the way? So what's the absolute value? So the absolute value of this is absolute value of this is absolute value of this, and this becomes the square root, the first one to the 2 plus the second one to the 2, which becomes 1. So the absolute value of this expression is 1. I can ask, for example, what is the conjugate of this? Yes, because that's a complex number. I can, in principle, ask every question that I was able to ask for complex number. So what is that? So this becomes the conjugate of this one becomes the conjugate of this one. So this becomes cosine. Let me write it in general. Do you agree? So that would be the complex conjugate. But I can write this as cosine of minus pi over 4, because cosine of minus alpha is equal to cosine alpha. I can move this minus sign in. But now if I ask you, can you write it in this form again? Yes, you can. This is the same combination, but instead of having pi over 4, you have minus pi over 4. It's a nice relation. So if you want to conjugate, you just conjugate the exponent. Yeah, so it becomes minus I pi over 4. So the complex conjugate of that number is this number, if you want to represent it in the this form. Okay. So let me write this formula here, because we want to work with this. So I would say that if theta is a real number, then e to the power of I theta is equal to cosine theta plus I sine theta. This is what we just learned, okay? Now, so far we had two representations of a complex number. One of them was the representation of the complex number in the Cartesian coordinates. Yes, that's just the normal. So if I give you z, you write x plus yi. So that's the standard representation of a complex number. But then we learned that we can write it in the polar form if we know what is r and what is theta. Yes. So here r is the absolute value of z, and theta is the argument of z, if you remember. So that was the second way to write that. But now you see this is exactly what is appearing there. So now we can write it in a really compact form, and might be this is the best representation of a complex number, and that's called exponential representation. So I just write r, and instead of this combination, I use that factor. So it's very compact and elegant. So this is now, it's called exponential representation. Representation, yes, of the complex numbers. That's crucial. So it's very nice and very compact. Yes, so that is, if I ask you to write a complex number in using exponential representation, what you need, still you need an absolute, the absolute value, and you also need the argument, but you can write it more compactly like that. What is the benefit of that? Everything comes automatically, yes? For example, if I give you two complex numbers, z1 with r1 e to power I theta 1 and z2 r2 e to the power of I theta 2. So you don't need to memorize an extra formula. Everything comes naturally. So what's your expectation? If I ask you to multiply them, you really don't need, of course, in principle, you should prove it, but it comes very natural. You multiply these two numbers, so it becomes R1, R2, and then you will start multiplying them. But because of the rules of arithmetic, you immediately realize you don't need at least to memorize. You would say that this is the same base, I write it, and I add these two together. Yeah? So I theta 1 is added to this one, I can factor I out, so this becomes this. Okay? So working with this is easy. But do you remember, if I wanted to do the same thing in the polar form, so you need to remember a formula for that, yes? Because if I want to just write them down, this would be the first one, the other one would be this one. It is not a priori clear. If I multiply them, yes, the first one is trivial. R1 will be multiplied by R2. But do you remember, we calculated, we need to multiply this by this by that, this by this, and this by that, and then simplify things. At the end, we realize that this becomes cosine theta 1 plus theta 2 plus I sine theta 1 plus theta 2, okay? So it was not natural. We have to do some calculations to reach that to that point. But it seems natural here, yes? Because we want to, of course, the proof why this is true is that one. Yes, because we already know that this can be written. So if I multiply them, we showed that this becomes this. But if I ask you what is this combination according to today's lesson, this is equal to that. Yes. So this is the proof of this one. But I mean, after proving everything, it comes very natural. You don't need to memorize anything. You can work it simply with exponential representation. So is that clear now, more or less? Okay, so what can I do for division? It's again natural. So I divide R1, R2, and then e to the power of I theta 1 minus theta 2. Because if I want to divide this by that, I need to write e and I subtract these exponents. Yes. Okay, let me write the formula for the nth root. So do you remember what was the formula for the nth root for complex numbers in the polar form? Okay, so this was the formula. If I give you a complex number, and if I give you a natural number, then if I ask you to write, what do I mean by this? This is not one number. Do you remember? This represents n numbers. And those formulas are, the formula corresponding to those numbers are the nth root. But do you remember I differentiate between writing this symbol and that symbol? Here I mean the principal root. Okay, so do you remember what was the formula? So it becomes cosine, and then you have I sine, and then the denominator is exactly this n that you want to calculate for the nth root, and then you have the argument of your complex number here and there. And then do you remember we have to add a factor of 2k pi here and there? And then if I ask you what k is, you would say that k is some number between 0 and 1, like an integer from 0 up to n minus 1. Yes? But now let us write this in this representation. So what can I write here? So this becomes the nth root of z. But this is exactly this combination that you see here, but theta has been replaced by this combination. Yes? So this becomes this e to the power of I argument of z plus 2k pi divided by n. So z to power 1 over n can be written in this form. Yes. I don't know. For example, if you want to calculate I to the power of 1 over 3, how should we calculate this? For example, let us do it in the exponential representation. The first thing we need to do is to calculate the third root of the absolute value of my complex number. But the absolute value of I is 1, and this is the principal third root of 1, which is actually 1. And then I calculate the argument. Argument is clear to visualize. Yes, I is in the imaginary part, so argument is nothing except pi over 2. Yes, the x. And then you put everything there. So I to the power of 1 over 3 is 1. The third root of 1. So the third root of this one, which is 1. Let me write it down. And then I have e to the power of I. My argument is this, but I need to write 2k pi and then divided by 3. But here k is 0, 1, or at most 2. So, okay, I have 3 numbers to write. K equals to 0. This becomes e to the power of I pi over 12. So this is one of them. So I don't know. Let me write W1, for example. This is one of them. And the other one, if I put k equals to 1, this gives me W2, for example. Let me call it W0 because of this, and then let me call it W1. And then if I put k equal to 1, so it becomes 2 pi plus pi over 4. It's 9 pi over 4, 9 pi over 12, which is 3 pi over 4. So it becomes 3 pi over 4. And finally, if I put 2, so this becomes 4 pi 17 pi over 12, yes? So these are, you see, it's more compact when you want to write something like, so these are the third roots of the identity, yes, of the imaginary unit. So these are the numbers, these are the only complex numbers, so that when I raise them to power 3, it becomes I. This is the mean. Okay. Another part of complex analysis is actually try to retrieve what we have in the real number. So for example, it's a good motive to be able to define e to power z for a complex number, yes? So it's not the full form, it's just a pure imaginary complex number we know about. But someone might say that, what is this one? E to power, I don't know, 5 plus 2i. What is the meaning of this combination? I have the exponential function, I want to raise it to power this one. You need to define it, okay? But you need to define it in a way that is consistent with your previous arithmetic. And of course, you need to define it in a way that when z is a real number, it gives you the same exponential from real analysis back, yes? That's the idea. So I think it's not hard. If you want to define it, for example, let me give you x plus iy. How do you think mathematicians will define this?
X plus or times whatever.
Yes, times. Yes, exactly. So you might say that, okay, if I want to keep the same arithmetic, so it should be like this, and then I would expect that this should happen. Yes, and now this one is exactly what we have here because y is a real number. So this becomes e to power x cosine of y plus I sine of y. This is not the proof. This is a motivation to define. Yes, so I would say that this is definition. So let z be equals to x, z equals to x plus yi be a complex number. Then, so e to power z is defined as follows. Is defined by this relation. So e to power z is e to power x times cosine y plus I sine y. Whenever you forget this, then you can immediately imagine that this is the same idea. So, and then you, instead of this one, of course, you're not allowed to forget this. And then you need to put this one there, okay? Okay, so let us explore some of these ideas. So first of all, let me ask you what is the, I don't know, a simple example. If someone asks you, can you write this in a standard form? So let me write this example. I don't know, for example, write e to power, we can say 3 plus pi over 3I in a standard form. So by the way, let me put a 5 here. Okay, so what can we do here? We can say that 5e to power 3 plus pi over 3I, according to 5 is 5. According to the definition here, this should be written in the form of e to the power of the real part, yes, multiplied by the cosine of pi over 3 plus I sine pi over 3. But of course, this is just 5e to power 3, and cosine of pi over 3 is 1/2, and the other one is the square root of 3 over 2 times I. So you multiply it, so it becomes 5 over 2e to power 3 plus square root of 3e to power 3 divided by 2 times I. So this is the standard form of that complex number that you see up there. Might be they give you this and they ask you to find the imaginary parts. So you need to write it in a standard form so that you are able to read the imaginary part. So they might give you this and ask you what is the absolute value. By the way, what is the absolute value of e to power I theta? What is that? Yes? You shouldn't think that much. This is a complex number, isn't it? If I ask you what is the real part, this is cosine. What is the imaginary part? This is sine. So what is the absolute value of any complex number? Its real part to power 2 plus its imaginary part to power. You need to think in that way, yes? You shouldn't let this complication actually distract you from that. So cosine squared plus sine squared is 1, so square root of that is 1. So this is independent of what you choose for theta. This absolute value is always equal to 1. Yes? Is that understandable or not? Yes or no? Yes? So I don't know why it sometimes takes a long time. So a complex number, what is the real part of this? Cosine theta. What is the imaginary part of this? This is sine theta. Yes? Okay. But if I ask you what is the absolute value of e to power z, what is your answer to that? So let us explore some properties of these complex numbers, of this new function. But let me start from the beginning. What do you expect? What do you expect if everything goes smoothly? What do you expect for e to power 0 in the complex numbers? Because 0 can also be viewed as a complex number. It is 0 plus 0i, yes? So what do you expect for this to happen? It should be 1. But let us check. Because when I write it in that form, it becomes e to power z plus 0i. So x is 0, y is 0. If I plug that in that formula, it becomes e to power 0 cosine of 0 plus I sine of 0. Yes, so that becomes exactly 1. But what do you expect for this? What do you expect for e to power minus c? Because you cannot take these, I want you to understand we cannot take these properties for granted, yes, because we are defining something completely new, even though it's similar to what we had before, okay? Of course, our goal is to keep the similarities as before as much as we can. So if this is going to work as previous exponential function, what should I be able to write in front for negative power test?
It should be 1 over e.
1 over 2. So this is what we expect, but it is not guaranteed, because we cannot say because we knew this formula for real numbers, we also know it for complex numbers. I just want you to understand that every step we are taking, we have to demonstrate it, okay? So how can we prove this formula, by the way? Let us see if it works or not. So if I want to work with this formula, I would say that let z be x plus iy. And then I put it here, so the left-hand side, I don't know, should we start from the right hand? Let us start from the right-hand side this time. Okay, so the right-hand side is equal to 1 over e to the power of z. Z is x plus iy, so I know the definition. So the definition is this. Yes? So what can I do now? This is a real number because x is real. So this one is the old friend of us, yes? E to the power of a real number. So I just write it down here. So here, can I bring it up and write negative or no?
Yes.
For this one. This one we know because this is just the normal exponential function. But this we need to convince ourselves. And that is actually simple because that's the division and you already know what to do. You just multiply it by the conjugate, yes, of the denominator. And then what happens? So here I will get e to the power of minus x, and then I have cosine y minus I sine y. And then the denominator, what is the answer? It's 1. Do you agree? Because this becomes the first one to power 2 minus the second one to power 2, but that becomes 1. Yes, hopefully you understand that immediately. So just let me write it here. Cosine y minus I sine y. So that would be my expression. Okay, but can I write it in this? This is the same trick always, yes? Instead of y, I can write cosine of negative y because cosine of negative y and cosine of y are the same. But instead of negative sign, I can write positive sine of minus y. So this is what I get for the right-hand side, yes? But what I get for the left-hand side, so the left-hand side is equal to e to the power of minus z. But z is this guy, so it becomes minus x minus iy, yes? So here I can write it as e to the power of minus x plus I times minus y. But this is again the complex exponential function. According to the definition, I need to write e. X is the real part of my number. The real part of my number here is minus x. And then what should I write? I need to write the cosine of the imaginary part plus the sine of imaginary part, yes? And then you see that these two are the same. So what we actually had before, this is also true. And we can go beyond that. So you can prove these things yourself. So if I have e to power z1 multiplied by e to power z2, I think it's important to prove these things. So this becomes e to the power of z1 plus z2. So essentially any property that we had before, it will be retained. Okay, so z1 divided by ez2, it becomes e to the power of z1 minus z2. So similarly, you can, this is a good exercise to improve your skills here. So you can immediately show that the same properties will hold. It's exactly like this. But instead of taking one z, you take one, z1 is x1, y1, you take z2 to be x2, y2, and calculate both sides and compare them together, okay? So this is working. But let me ask you one more question. So what can I write? So if z is equal to x plus iy, then, so let me write it in this way. If z is this, then what can you say about absolute value of this? Can I write something nice in front of it? What is that?
Square root of x squared plus y squared.
No. I mean, simplified version of all the things that you are doing in your head. You see, here, e to the power of z is equal to e to the power of x cosine y plus I sine y, yes? What can I do? First, if I ask you, one way of doing it, the long way, is to, if I ask you what is the real part of e to power z, can you answer? What is the imaginary part? You see, whenever I ask you about absolute value of a complex number, you need to think about the real part and imaginary part. Yes? So what is the real part of the e to the power of z? Can you read it for me?
E to the power of x cosine.
Yes, e to the power of x cosine y, yes? And then what is e to the power of z? It's e to the imaginary part is e to the power of x sine y, yes? Now these are no longer complex functions. These are just real functions because x and y are real. Okay, and then if I ask you what is the absolute value of this, you need to write square root of the real part to power 2 plus the imaginary part to power 2, yes? But this is easy to calculate, yes, because this becomes e to the power of 2x cosine to the power of 2y, and this becomes e to the power 2x sine to the power of 2y. I can factor e to the power of 2x out. What is left for me is cosine squared plus sine squared, which is 1, and this is the case. And then what is the answer to this is just simply e to power x. Yes? So it is simple. Whenever you have this and someone asks you about the absolute value, it becomes the normal exponential function, e to the power of the real part. So if I want to write the formula, it's nice. Some folks write it independent of writing this. They write it as e to the power of real part of z. So if I ask you what is the absolute value of e to power z, you write it as e to the power. I mean, instead of writing x, what is x? X is the real part of z. So you write e to the power of real part of z. Yes? But what is your expectation about this situation? I calculate e to power z, and then I take the complex conjugate. Can I write something nice in front of it? Let us check, yes? So how should I check that? And by the way, I wanted to tell you another way of doing this, much simpler. So if I want to calculate absolute value of z, do you remember what should I do? This is a product. Do you remember I told you that the absolute value of the product is the product of absolute values? So this becomes the absolute value of this one multiplied by the absolute value of that one. But what is the absolute value here? Yes, immediately. What's the? It's what?
Well,
It's 1. And what is this? Is exponential function. Exponential function in the real numbers. So you know that e to power x for real numbers is positive, so it becomes e to power x multiplied by 1, and that's exactly the same result. So it's better to do it in that way. By the way, I forgot to say, in the real numbers, there is a very big difference between exponential of real numbers and exponential of complex numbers. What that is, in real numbers, it is not possible to have e to power a real number negative. But we just saw that, yes? E to the power of I pi, if you remember, the famous, the most beautiful mathematics equation, this becomes equal to -1. That's negative, yes? So in the real numbers, if I have e to any power, even if the exponent is negative, the answer is positive. But in the complex numbers, don't think that exponential functions should always be positive. No, some exponential functions, depending to this exponent, you might get a negative number at the end. Yes? But this cannot happen here for this part because e to the power of x, this is just a normal exponential function. And that's always positive. Okay. So let us go back now to ask the same question here. So what is the point? Can I write something nice in front of it? E to the power of z, then I want to conjugate the whole content. So we will see that this is very nice. You just write e and then conjugate the exponent. Okay, so that's a very nice formula. We want to explore that. So how should we explore this, do you think? What's the best way to do that? Hmm? Okay, we can just do the same as before. So we say that we can calculate both sides actually to confirm that this is indeed the case. So for example, what can I do here? I can write that e to the power of z. So I would say let z be equals to x plus iy. And then this means that e to the power of z becomes that expression that I wrote, e to the power of x cosine y. Let me multiply it, plus I sine. And let me, by the way, we had these formulas before, so let me just use them. So what I do, if I want to take the conjugate of the whole expression, I need to conjugate this one and conjugate this one, because if you remember, we had a formula, z1 times z2 totally conjugate is the conjugate of the first one multiplied by the conjugate. It was not trivial, but it came up to be true. So that is the correct one. So I will take the conjugate of this one. What is the conjugate of this one?
Just the
That's itself, because that's the real one. So this becomes e. And then what's the conjugate of this one? The conjugate of this one is cosine y minus sine y. But this is clear what we can do. We can write it as e to power x. Again, the same trick. Instead of cosine y, I write this. Instead of sine y, I write this one. And then if I ask you what is this one, this is the e to power x minus yi. Do you agree? If I ask you to write this back in the form of the exponential function, you write this. But now if I ask you what is this, you immediately realize this is nothing except z bar. So we started from ez totally bar, and then we reached the e to the z bar. Yes, so that's actually a very nice result. Okay, there is a very big difference now. If you are working with real numbers, if I tell you that e to power x1 is equal to e to the power of x2, when you are working with real numbers, what you can conclude about x1 and x2? They are the same. But this doesn't happen here. You can conclude that x1 is equal to x2. But if e to power z is equal to e to power w, and z and w are complex numbers, you cannot conclude that you cannot conclude that z is equal to w. Might be z is equal to w, but it is not guaranteed that. But can we say better? Can we say something better? Okay, you say that they are not equal, but can we say something which is always true? Equality is among those possibilities, yes? But what can we write? Let us explore that, yes? Before exploring that, let me ask you one question. If this is exactly the same thing, do you remember, if I ask you, be careful about these things, if you want to go everything automatically, you will be in trouble. If I ask you solve this equation, what is x in real numbers? It's 0. But now if I ask you solve this one, if you say z is 0, this is not generally true. Of course, it doesn't mean that if z is 0, it is not right. Yes, 0 is one of the possibilities, but we have more. We want to explore all of them. Let us explore them. Okay, so let me ask you to solve this. Solve the following equation on C. And the equation is this. You want to find all possibilities for that. So how should we solve this, do you think now? It's clear, one of the answers should be 0, but Are there more answers to this equation? We need to explore. Where do you start? Yeah, there is no way, because that's definition. We have to start with the definition. I would say let xz be equal to x plus I y, and then my goal is to find x, my goal is to find y, because if I succeed to find x and y, then I have my z. Okay, so how can we do that? E to power z is equal to 1, so it means that e to the power of x plus, so let me write it, e to the power of z. What is the definition? The definition is this. By the way, how many answers do you expect for this? How many complex numbers do you think will satisfy at the end? It's infinitely. There are infinitely many, yes? So what's happening here now? It means that if I want to solve this equation, so 1 is another way of writing 1 is to write it in the complex form. The left-hand side is a complex number, the right-hand side is a complex number. They are supposed to be equal. So the real part should be the same, the imaginary part should be the same. So this means that the real part, which is this one, should be 1. And the imaginary part, which is this one, should be 0. Yes? But be careful now. These are normal functions. Yes? Normal exponential function, normal sine and cosine function. So everything is in the real numbers. So let us start with this simple one. That's the zero product rule. Either the first one is 0 or the second one is 0. But in real numbers, the first one cannot be 0. So there is only one option available here. Yes? So x is real, so e to the power of 0 is always, e to the power of x is always positive because x is real. So this means that definitely this should be 0. Y is 0, so we are, if you work in the unit circle, I want to have the sine of y to be 0. I'm asking you about y. So, but you know that sine is related to the y coordinate. So either you should be here or there. So it means that any multiple of pi is acceptable, because even multiples of pi are here, odd multiples of pi are here, but all of them are acceptable. So I would write y is equal to n pi. Yes? And if someone asks you what n is, you would say all possible answers here. But then we realize that, so let me, if you don't mind, let me write k here for some reason. You will see why. So let me change the name to k here. Okay, so it means that y should be this. But one of these points is not acceptable. Which one and why? Because you have two equations to satisfy. This is only for this one, but we also need to care about this one. But e to the power of x in real numbers is always positive. And the product of these two is supposed to be 1, which is also positive. So it means that cosine of y has to be positive. And if you choose this point, cosine becomes negative. Yes? So if you want to consider only this one, all of them are acceptable. But if you want to consider both of them simultaneously, which we have to, then k should be an even integer, not an odd integer. So this means that considering this, taking this into account, k should be 2 times n when n is a natural, is a complex, is an integer. So this means that y should be 2n pi, where n belongs to z. But still, I need to find my x. So what should I do? When I realize what is this, I put it back into this equation. So this becomes e to power x cosine 2n pi is equal to 1, and I need to find x. But cosine 2n pi, what that is? Cosine 2n pi is nothing except 1. So it means that I need to solve this equation. But this equation is not this equation. It's not a circular argument. This was, here z was complex, but here x is real. There is only one solution for this equation, and that is 0. Yes? So now I was looking for z. Z is x plus iy. I got x equals to 0. I got this one to be 2n pi I. So that's it. So now we have your solutions, all your solutions, infinitely many solutions. I, and then n is an integer. Even negative integer is acceptable. So you have, this is your solution. There are infinitely many solutions for this very simple equation. So this is a very big difference between complex exponential function and real exponential function. Yes? So now what can you say about this one? Can you tell me what is happening now if I have this situation? If I have e to power z equals to e to power w, what can I conclude about z and w? Of course, one possibility is that they are equal, but there are infinitely more possibilities available. So what can I do? I don't want to start everything from scratch. You can use this result to say something about that. How can I connect this problem to that problem? How can I bring in 1 here? In that problem, 1 is absent. In this problem, I need to have 1. So what is the natural step to do?
We replace e to power z with 1.
No, because z is given, I cannot replace it. But I can write it in this form. Let me write this to see if you agree with me or not. Do you agree from this I can conclude this is 1? Yes, because if they are equal, it means that e to power z divided by e to w is 1. But another way of writing this is this one. Do you agree? So this, from here, I conclude this one. But if I ask you what can you say about this exponent, you already know. If e to some power is 1, you know what is happening for the power, yes? So here, e to some complex power is equal to 1. So this means that z minus w is 2n pi times I, where n is an what? So this is the main difference. In the real numbers, if this is happening, z has to be equal to w. But in this case, we have infinitely many possibilities. And another thing is that, is this function periodic? E to power x in the real numbers. Is e to power x periodic? It's not, yes? It just as a line goes up. But this function is periodic. Yes? Why? Because if I ask you, by the way, if I ask you what is e to power x plus, let me write it in this way. If I ask you what is e plus z plus 2n pi times I, if I ask you to calculate this, yes, what happens? It becomes e to power z itself. Do you agree? Because the difference between these two is an even multiple of pi times I. So this is periodic function, and the period is complex. So what is the fundamental period? The smallest period, the smallest value is when I choose n equal to 1. So this would be the period of that function. And the period is also a complex period here, yes? So you need to think abstractly. There is nothing that you can imagine because we don't have the graph of that available to see if it is repeating itself or not. So it is by definition of a periodic function, it means that if I can find a t so that if I add it to z and I calculate the function, it gives me the same value of the function. This is the meaning of a function to be periodic in abstract way, yes? In real numbers, we can visualize it, that something is repeating, some pattern is being repeated. But here, we have to choose the abstract definition. Okay. By the way, let us solve an equation together here. So let me give you another example. So you shouldn't be surprised. If I write e to power, so if I ask you to solve this equation when you are doing Math 2C or 3C, what is your answer to this? Solve this equation. There are no answers, yes, because e to the power x cannot be negative. But don't think this can happen in complex numbers. So these bizarre things you should expect in complex numbers. So we want to solve this equation in the set of complex numbers. Let us see if we can find solutions, yes? Okay, how should we solve this equation? Exactly as before, I would say that let z be equals to x plus iy. I'm looking for x, I'm looking for y, okay? So what should we do? If I plug that into that equation, then it means e to power x cosine y plus I sine y is supposed to be equal to -2. Yes? What I say that, I would say that this is a complex number. This is also a complex number, yes? I myself preferred, if you remember, I did the same, more or less the same thing when I was talking about the roots of an equation. So this is a complex number on the left, that's a complex number on the right. If they are supposed to be equal, then the absolute values have to be equal, yes? What is the absolute value of the right-hand side? Can you tell me? It's 2. What's the absolute value of this one? We just had it. E to the power of x. So I want you to understand the logic. The logic is that if this is equal to this, then it has to be, because if this is not the case, this cannot be satisfied in the first place, yes? But this I know. What is x here? Be careful. X and y are real, so you are working in real numbers now, momentarily. So what is x? ln of 2. So yes, we got it. X is ln of 2. By the way, it's a little bit strange. So if I give you e to the power of z, so you see here, if you want to write ln of -2, ln of -2 is not defined, yes? But this is the real part. And then what I do, I go back, instead of e to the power x, I put 2. Yes? And then instead of -2, I just put -2. And now I can divide everything by 2, so cosine y plus I sine y becomes -1. But then this gives me a system of equations. This gives me that cosine y should be -1 and sine y should be 0. Okay, so I want all of them. All the y's that cosine y is -1 and sine y is 0. What are they? So which part of the unit circle you are? On which part? Cosine is the x coordinate, so you are here. Yes. So it means that y is an odd multiple of 2 pi. Odd multiple of pi. So odd multiple of pi means 2n plus 1 pi. Yes. So n is an integer. Okay, so the answer is z equals to x is ln of 2 plus y is this guy multiplied by I, n belongs to z. So you see, this is a nice way of solving this equation. So there are infinitely many answers for this simple equation. Yes. So here we didn't have even one single solution. But if you want to solve similar equation in the complex numbers, then suddenly we get infinitely many solutions. Yes, all of them are acceptable. Let me see if there are some things that we can continue later, but let me just motivate this. It is one of the exercises in the book, but let me ask you one question. How do you, if you are a mathematician, how do you think you define sine z? Yes, z is a complex number. For example, what do you think about this? It's a little bit strange, but you want to define something for it. There is no reason behind that, but you need to motivate your definition. How do you motivate your definition here? Yes?
I use the addition formula for sine.
Yeah, that's a nice starting point, by the way. But then there is a problem again. How can you solve that? Yes, that's a very good starting point. Thank you. So instead of z, you write x plus iy. Then because you want to take everything intact, so you would say that this becomes the sine of the first one, cosine of the second one. Yes? Plus sine of the second one, cosine of the first one. But the problem is still the same. I don't have any problem here, I don't have any problem here, but still I have problems here because those are complex numbers. So it means that you are right. You actually moved forward a little bit. If I can define this simpler version, then using this, I can define probably the other version. Okay, but let me ask you something. This definition, we can finalize this today. Okay, so here, let me ask you something. What can you write in front of it? Theta is a real number. What can I write? We learned today. What can I write in front of it? I can write cosine of theta plus I sine of theta. Yes? But now let me immediately ask you this question. Z belongs to R. Oh, sorry, Z belongs to C. What do you write in front of this?
times.
Yes. So I mean that it is not immediately clear. If someone writes this, you should be very careful in writing this. Yes? Because here I'm assuming that theta is in R. This was what I tried to motivate you is correct. But because this is correct for a real number, it's not guaranteed that this is also true for a complex number. It might be true or might be false. If you want to use it, you need to prove it first. But it turns out that this is also true. Okay? So this is also true. And I want together to show this. Even if, so let me emphasize here. So you don't worry about that. Whatever you have in the exponent, you can simply use this formula. So why this is true? Because let z be equal to x plus iy. Do you agree? Then e to power iz becomes e to the power. I have to multiply I by z. It becomes ix. I times I is minus y. This is the case, yes? But what should I write now? This becomes e to the power of... so how should I continue? So it becomes e to the power of minus y plus xi. Yes, iz, I multiplied I here, it becomes ix, I multiplied I there, it becomes -1, and I just replaced them. But this is the normal exponential function, we know about it. So what can happen here? So let me see if we can actually prove it. No, we cannot prove it because we don't know the definition. Yes, so that is the definition or not? Okay, so this is not, sorry, we cannot prove it. This is the source of the definition of sine and cosine. Yes, so so let me think a little bit. So here, this more or less we know the result, but should we understand this? No, we cannot prove it, because if I want to prove it, I want to show the left-hand side is equal to the right-hand side. Yes, I don't have any problems with the meaning of the left-hand side, but still, right now, I have problem with the meaning of sine and cosine for complex numbers. So I am not at the level to ask you to prove it, because if I ask you to prove it, it means that you know the meaning of that, which of course you know. You need to know the meaning of these two, and then say that, okay, this meaning is the same as this one, which we don't know. This is the source of definition for sine and cosine. So you see, we define, so if this works, then what happens for this one? If this is true, then this, instead of z, you put minus c, but there is no difference between them. And now see what happens if I add them together. This one and that one are gone. So cosine z plus cosine z becomes 2 cosine z. This one plus this one, and I divide by 2. So this is the source of definition for cosine z. So I would say that this is the motivation behind the definition. There is no proof here. Yes? So I am saying that we knew that this formula is correct we know that this formula is correct for real theta. Okay? Let us, this is the logic. Let us define sine and cosine in a way that this formula remains valid even if z is a complex number. So do you understand this is the logic. The logic is not to prove this. We cannot prove that, yes? But the logic is to define sine and cosine in a way so that this formula remains valid even if z is a complex number. This is the logic behind that. And if this is going to be valid for z, it should also be valid for minus z. This gives me this, and then I add them. This one and that one are gone. This becomes 2 cosine z. This one plus this one is this, and then I divide by 2 to find cosine z. So this is the source of definition. So cosine of z is a little bit strange definition. It has nothing to do with the unit circle or whatever. It's completely related to the exponential function. So this e to the power of iz plus e to the power of minus iz divided by 2. It's extremely important. So that is definition. So what is the definition for sine z? Instead of adding these two, this time I subtract these two. This one minus that one. Why I subtract? Because this one and that one are gone. This one becomes positive I sine z, positive I sine z. It becomes 2i sine z. And then sine z becomes e to the power of iz minus e to the power of minus iz divided by 2i. This is also definition. So what I wrote here is not the proof of this. We cannot prove it because we don't know what they are. This is the logic that how we define sine and cosine. So the definition of sine and cosine here has nothing to do with the unit circle at all, but we need to check consistency. Yes, because I am not allowed to just write sine because everyone knows something about sine. So it reminds you about something. How can I check the consistency that this is a good proof? This is a good definition. It's a consistent definition.
You may take a complex number with only a real part.
The real part, and it should go back to the normal sine function. Yes, do you understand what's the logic? So the logic is not proof at all. So here, let us check. If now use this definition, let us calculate cosine x. Let us calculate cosine x. This can be written as cosine x plus 0i. Yes, if everything is supposed to be consistent, this should be the case. And now I can use this formula. Let us see what happens for this formula. This becomes e to the power of I times z, which becomes I times x, plus e to the power of minus ix divided by 2. But this one is this one which we had some kind of proof for that. Of course, the proof was not the real proof because this is a little bit higher than the level of this course, but we had some kind of proof for that. So if I put that back here, what happens? The left-hand side becomes, this becomes e to the power cosine x, I sine x. The other one becomes exactly cosine x minus I sine x, because that is minus x divided by 2. So you see that this one and that one are gone, and this becomes exactly the cosine. So cosine is equal to cosine is not contradiction. So this means that the point is that if we define sine z and cosine z in this way, first of all, nothing is inconsistent. And the good point is that we can extend this one to consider every complex number, which is actually a good thing to do. Yes. So the properties of sine and cosine are not similar to the properties of sine and cosine that you had already. But whenever z is a real number, this goes back to the old definition. Yes? Just one thing here. So for example, sine of z equals to -10 has an answer here. But we didn't have any answers like that because sine cannot be less than -1. Okay? We will talk about this part on Friday if everything goes good. Yes? And then I don't know, on week 23 we have one session. I don't know if you want to continue week 23 as well or not, but then we can solve harder problems there. Yes? Yeah, thank you very much. So I end this stream here. There are 4 people online. I will be on Zoom if you have any questions for a moment.